Every year, high-stakes exams determine the futures of millions of people. And every year, these systems fracture under the pressure of mass leaks, unauthorized access, and coordinated cheating networks. These failures happen for a specific reason. The vulnerability is built directly into the system's DNA, because the final exam exists long before a single candidate sits down to take it. To see how this happens, look at the standard life cycle of any major test. Human experts write the questions. The final paper is compiled, stored on a server, sent to a printing press, packed into boxes, and shipped across the country to thousands of local testing centers. This diagram maps that entire process. Over this extended span of time and physical space, an exploitable supply chain is created. Any point under this red bracket represents a window where the master paper can be copied, stolen, or compromised. We can eliminate this entire window using just-in-time procedural generation. We can engineer a system where the final exam is never created until the exact moment the test begins. This requires moving the security model away from relying on humans to keep a secret and toward a framework of mathematical verifiability. If a compiled master document sits in a vault or on a hard drive anywhere in the world, the system can be breached. The only guaranteed defense against a leaked paper is to ensure that paper never exists in the first place. How do you evaluate millions of students simultaneously if there are no actual test questions stored in the central database? The traditional fixed question repository dissolves into an interconnected web of abstract data nodes. Each node stores rule sets for subjects, difficulty, and logic. A single baseline template within the node swaps variables, scenarios, and numerical values to generate distinct iterations of the exact same problem. Through this mathematical variation, one conceptual blueprint yields millions of highly unique, unpredictable questions. System administrators are restricted to managing the psychometric calibration data. They set the rules for what the exam should test, but they never see the specific questions produced. If an intruder manages to breach the central servers, they won't find an answer key. They only extract raw logic parameters and abstract formulas. Even the architects who design the test do not know what questions will actually appear on screen. Replacing rigid text files with mathematical templates erases the central master test paper. Without a master paper, traditional theft vectors are immediately neutralized. To select and build questions from billions of possible variations, the system requires a massive random seed to trigger the generation process. Standard computer randomness generated on a local server is a severe vulnerability. If an algorithm relies on the server's internal clock, the skilled actor can compute the seed. A corrupt administrator with access to that local server could manipulate the entropy to trigger the generation early and capture the exam. We pull entropy from a decentralized ledger, waiting for a future hash. It's mathematically impossible to calculate before the network mines it. The generation pauses until this block finalizes. Then the hash drops, feeding directly into the knowledge universe as a seed crystal. This completely blindfolds the exam creators. They are entirely locked out of their own system's generation sequence until the network produces the hash.
By outsourcing the random trigger to public infrastructure, central authorities are stripped of the power to leak the exam. This creates true trustless entropy. The exact moment the blockchain hash strikes the system, the generation begins. This data packet rapidly navigates the architecture to assemble the exam. That unpredictable hash instantly triggers a real-time, multi-agent AI pipeline. The AI orchestrator loops specialized agents in milliseconds. One selects a concept, another generates scenarios and formulas. Quality control agents then verify mathematical correctness and scan semantics for clarity. Finally, a parity validator ensures strict difficulty standards are maintained across all variations. This entire orchestration happens at extreme speeds. The final questions are compiled mere seconds before they appear on the candidate's monitor. The result of this pipeline is that every single candidate in the testing center receives a completely unique, dynamically generated examination. If a candidate uses a hidden camera to broadcast a question to the outside world, that information immediately hits a dead end. Because every candidate's exam path is distinct, a leaked question has mathematically zero utility for anyone else. Coordinated cheating networks become obsolete. Securing the server is only the first step. The most vulnerable point in any digital network is the physical endpoint terminal where the user sits.
If a terminal is compromised with specialized malware, an outside expert could hijack the session and answer questions on behalf of the seated candidate. To counter this digital bypass, the system deploys hybrid behavioral validation. Here is how the validation executes. The digital test pauses at 80% completion. The system pulls a second, fresh blockchain hash and routes it directly to a local printer. This hash generates an offline control set of questions, printed and answered manually. The system then overlays a bell curve, comparing online digital performance against offline paper performance to search for drastic capability discrepancies. By forcing an unhackable physical baseline check at the end of the digital exam, the system exposes behavioral mismatch. External digital assistance is caught, locking down the digital to physical endpoint. The final phase of the examination lifecycle occurs the moment the candidate submits their finished test. This raises the issue of post-exam data manipulation. How can a candidate prove their score wasn't altered by centralized authorities after submission? This visual shows the creation of a cryptographic commitment. The uniquely generated questions, the candidate's specific answers, and exact timestamps are bundled together and processed through a hashing algorithm. Anchoring this receipt to the blockchain gives the candidate a permanent, mathematically verifiable audit trail of their exact performance. While this architecture eliminates mass leaks, operational risks do remain. AI fairness calibration, physical hardware compromise, and implementation bugs require active governance. However, these are localized, manageable challenges. They are entirely different from the unrecoverable nature of traditional pre-exam leaks. This architecture provides a technical resolution to a human problem. By eliminating the master paper and replacing it with real-time generation, the system moves from a reliance on human secrecy to a reliance on mathematical verification.